Hello everyone. Today we're on tutorial 8, first year university physics, rotational motion. Okay, let's go to my notes. I'm going to show you the notes quickly and then go to the whiteboard to go through things with you step by step. So the first part starts with the analog of work for rotational motion. The next defines the moment of inertia for the simple case of a number of particles rotating. Then we want to go to the analog of Newton's law. So you'll have my notes on the screen. Now what I'll do is I want to go through these notes step by step on the whiteboard. You can write that out. Rotational work, energy, and momentum. But number one, let's do a formula for the work done in rotational motion. So let's imagine a little particle, a little point that moves at distance s, which is the arc length. This is theta, the angle, my radius. Now, I can imagine a particle here, and I have a force acting on that particle and pulling it along. Let me draw that better. It has to be at right angles in this simple case. So this should be at right angles to the radius. Right, so I have my formula for, my normal formula for work is force times distance. I'll do it in terms of magnitudes, not in terms of vectors, although the force is a vector. For simplicity, we'll just do it in terms of magnitudes. And emphasize that the force must be perpendicular to the radius in this derivation. I'll briefly show you a more general definition, although it's a little bit advanced and not something that you're going to do in your first year tutorials. Before I do that, let me use a formula for the arc length, r theta. Substitute into here, work done is F r theta. And then I'm going to define Fr to be this quantity tau. And I can write tau theta. You can see how this is analogous to the linear formula. A linear force times essentially a linear distance. This is the angle covered, and this quantity here is what's called the torque. It's a torque or a turning force, if you like, or turning force. So this is my first important formula. The next thing is to define the moment of inertia. So let me clear this. I have another screen up so I can remind myself of my notes. Number 2, moment of inertia. To derive a formula for this thing, you consider an object, and I'll just pick an origin anywhere, and we'll let the object rotate. So you can see that every particle in this object is going to rotate with the same angular velocity. So I'll pick a few points, and I'll imagine this object to be made up of distinct points. Now, there'll be a linear velocity. Each particle will have a linear velocity. We call that v1. It'll be a distance r1 from the axis of rotation. And I'll imagine this little particle to have a mass m1. Then this one be v2. What I will aim to do is to obtain a definition for the moment of inertia and also a formula for the kinetic energy. Let me try and write the two a little bit clearer. V2, and this one I'll call it a general, give it a general name. So I'll call this one mass 2. This is really not very visible, is it? Let me rub this out. Let me draw that again. So let me call that V2 R2. This one is a general one, so this one is M, capital N, and from the origin should be a right angle here. This distance here will be Rn, and this velocity V capital N. Now let me write the kinetic energy for all of these. Basically, add up the kinetic energy for all the particles. And I suppose, for simplicity, we have a number n of particles. It's obviously going to be very, very large, but we only need to consider a few. So my rotational kinetic energy is the energy of all these particles. So this is a half m1 v1 squared plus a half m2 v2 squared. And I add all of them up to, this really goes to a very large number, but we'll just pick a few points. Mn Vn squared. Now from your tutorial on and your lectures on circular motion, we know that V is equal to R omega. So if I substitute for V in all of this, I have K rotational equals a half M1 R1 squared omega squared plus a half M2 R2 squared omega squared plus a half Mn, not R, Rn squared omega squared. Now you can see that omega is going to be the same. In terms of the angular velocity of all the particles, it's the same for every particle. The linear velocity will be different for the different particles depending on the radius, but the angular velocity will be the same. So I can take out a half omega squared as a factor, and inside I'm left with m1 r1 squared inside the brackets plus m2 r2 squared plus mn rn squared. Now I'm going to define this quantity to be the moment of inertia, which with a symbol I. Now, defining this as the moment of inertia, I'm running out of space. I'm going to draw it down here. Then I can write my rotational kinetic energy as a half I omega squared. And you can see how it's similar to the formula for the kinetic energy for linear motion. And in fact, what you're going to see And even when with circular motion, for every formula for linear motion, there is an analog for rotational motion. Here we're replacing mass by this quantity, the moment of inertia. For a system of particles, the moment of inertia is given by this. But we're going to see that for different objects, the moment of inertia will vary according to the shape of the object. We'll come to that. So this is then my definition of moment of inertia for a system of particles, and the important definition of rotational kinetic energy. Let me clear this, and let me shift my notes and go to the next. The next thing is to obtain another important formula, the analog of Newton's law for rotational motion. This is number 3. Alright, so let me consider again motion in a circle. I'm going to consider the motion in this direction. Doesn't matter which direction, it'll be the same either direction. My omega in this direction. My omega is going to vary, so this is not. Let me just say that's the direction of rotation. This is my initial velocity, angular velocity, my final angular velocity. Now we know that by Newton's laws, second law, that in order to change the velocity, we need a force. Newton's first law. So we apply a force here to change the velocity from an initial velocity omega I to a final velocity omega f. Now the work done is equal to the change in kinetic energy this is the change in rotational kinetic energy, omega f minus so the work done by rotation then is a change in the rotational kinetic energy. And from my formula before, my work done is the turning force. Remember Newton's first law, every body continues in its state of rest or of uniform motion in a straight line unless compelled to act otherwise. So if we're going to change the velocity, we have to have a force acting. And in this case, it's the torque. So that's T theta. Tau theta. This is the Greek letter tau, so I should be careful to pronounce it correctly. My formula for rotational kinetic energy is a half I omega f squared minus a half I omega I squared. I can take out half I as a factor. Now I'm going to assume the torque is constant so that the acceleration is going to be constant. And then from circular motion, if you recall your constant acceleration formula, this is angular acceleration. My angle theta is equal to minus f squared minus omega I squared. So I can substitute this into here. So I have tau theta equals a half I, substitute the stuff in brackets, 2 alpha theta. Now you can see that my thetas are going to cancel, and what I'm left with, and my 2's cancel, so what I'm left with is the tau equals I alpha. This is my moment of inertia, my angular acceleration, and my angular force, the torque. This is the analog of Newton's second law. Force is equal to the rate of change of momentum, which comes to F equals ma. Okay, that's number 3. By the way, you can do the same derivation starting with the work energy theorem for linear motion. It's in my notes that I showed you before, but I think now we go on to, what's the next section? We have a look at my other screen. Oh yes, the important radius of gyration. Before leaving this subject, let me just mention that inertia. Inertia is the resistance of a body to motion. So the heavier something is, the more difficult it is to start it moving. And similarly, with rotational motion, the bigger the moment of inertia, the more difficult it is to start a body rotating. So we have the interpretation of mass as a kind of an indicator of the resistance to motion, and again the moment of inertia as an indicator of the resistance to movement. Let me clear that and define the radius of gyration, and I think I've called that 4. Radius of gyration. To define the moment of inertia. So just to keep the formula for moment of inertia looking sort of similar to the original definition for a system of particles, we define this quantity. This quantity will vary according to the shape of the object. If it's, for example, a solid disk, or if it's a sphere, or if it's a hoop, the radius of gyration will differ. Not very straight lines, but anyway, this gives me, let me just change my pointer. This is a table of the moments of inertia for different objects, from which we can obtain the different radius of gyrations for the different objects. So if I start with the point mass, the moment of inertia is just mr squared, just a radius squared, the ordinary radius. So if I compare with my definition of the radius of gyration, I equals mk squared, then k squared equals r squared, so k is equal to r. When I come to a hoop, the moment of inertia is given by mb squared, but again for a hoop, b is the radius. The radius of gyration is equal to the radius. So for these two cases, the radius of gyration is just a radius of the circular movement. Now when I come to solid disk now, my moment of inertia is a half b squared. So if I compare it with mk squared, then my k is equal to b over the square root of 2. For a solid sphere, it's 2/5 mb squared. Comparing with I equals mk squared, I square root the b squared under 2/5 to get my k is equal to this. For a solid cylinder, it's a half b squared, which is similar to a solid disk. So again, my radius of gyration is also similar, b over root 2. When the cylinder is very thin, however, and here I'm rotating about its axis. Here I'm rotating through the middle, so it's rotating like this, in which case the moment of inertia is given by this. And again, by comparing with my definition of radius of gyration, I get k is equal to this one. Finally, number 5, I didn't number this one, but it should have been numbered. Maybe this could have been numbered number 5. and this one number 6. This is angular momentum, again another important quantity. The moment of inertia times the angular velocity gives me the angular momentum, which is, the normal symbol is L. Again, you can see it's the analog of my linear momentum as mass times velocity. Now I'm going to do this with you because it arises in certain problems. And so it's useful for you to have an idea of some of the features of rolling motion. Let me first show you my notes so you can look at them yourselves later, but I'll do this on the whiteboard again. In particular, we want to see that the linear velocity of the center of mass is equal to the tangential velocity. And then the final bit is an example of the velocity at different points on the circle. We'll come to that. So let me stop sharing and go to the whiteboard. Not too great, but a bit better. This rotates. Let me look at this arc length here. So let me call this distance S. As this rolls, this is going to move to position here. So this is a distance S. Now what I want is a relationship. The linear velocity is going to be the velocity of the center of mass of the rolling body. This is my linear velocity. I'm going to call the tangential velocity by the same name. Now what we want to show is that the tangential velocity is equal to the linear velocity. Now this distance, by the formula for arc length, is just r theta. And my tangential velocity is the tutorial that you would have done before. And I will do unrecorded lectures at a later time. This is equal to V, which is equal to R omega. I call my radius R, and this is the angle theta there. Now, you can see that my center of mass travels from this distance to this distance. So the center of mass has traveled a distance s. So my velocity will be s over t. And now s is equal to r theta. And theta over t is my angular velocity. So you can see that my linear velocity of the center of mass is equal to r omega, which is the same as the tangential velocity. So we conclude that I'm going to do my conclusion over here. Linear velocity of the center of mass is equal to my tangential velocity. Now let's look at the motion of points on the rim of the disk or on the points of the circle. I'll go to the whiteboard to show you this. Right. So let's look at our rolling disk. Now we've looked at the velocity of the center of mass, and we found it to be v equal to the tangential velocity. Now I want to look at the motion of a point on the circle. Let me call this point A, and let me find its velocity. And let me look at another point here, B. I can do this for anywhere on the circle, but it's a little bit more complicated because of the angles. So I'm going to pick these two simple cases. You can do the rest yourselves once I've shown you how to do this. Now, at this point, it has the velocity of the center of mass, but it also has a tangential velocity. So the point A is going to move at twice the tangential velocity. So we have the v, the linear velocity of the center of mass, plus the tangential velocity. So we end up with 2v. Now, if we look at point B now, you might think of it yourselves. How fast is this going? We have the velocity, the tangential velocity now is in this direction. The linear velocity of the center of mass is in this direction. Let me draw the tangential velocity at this point so as not to confuse it with VB. Sorry. Okay, let me just see what the value of VB is. So we're moving in this direction, the tangential velocity, this direction, the linear velocity of the center of mass. The velocities are going to cancel themselves out, so we're going to get 0. So this may seem strange, but this point has no velocity. I'll let you think about that. To finish up, the accelerations. We've seen that the tangential velocity is equal to the velocity of the center of mass. What about the acceleration of the center of mass? So my velocity for the center of mass is equal to the tangential velocity, so it's r omega. So the acceleration of the center of mass is going to be A equals v over t, which is r omega over t. So this just equals r alpha. So my acceleration of the center of mass is equal to r alpha. I can also do this in calculus using the definitions, the instantaneous definitions of acceleration. Using calculus, we define the velocity to be the rate of change of velocity. So we define acceleration to be the rate of change of velocity, and we define the angular acceleration to be the rate of change of the angular velocity. So we have dv by dt. This gives me my linear acceleration of the center of mass. This gives me my angular acceleration of the center of mass. So we end up with the same relationship. This definition allows us to define the acceleration at every point of the motion. Now let's go to the very important topic of total kinetic energy. which you will need for many of your tutorial questions. Total kinetic energy. Now KE total, as you might guess, we certainly have the linear velocity, but there may also be rotational energy due to rotational motion, as well as kinetic energy due to linear motion. There could be kinetic energy as well due to rotation, and my formula, omega squared. This is my very important formula. Now you may have a number of objects, not just two, so I'm just applying to one object, but in a particular problem you may find a combination of objects, and you may then apply conservation of energy. There'll be some examples in your tutorial sheet of this. Now normally in a problem, it's convenient to use this formula, V equals R omega. The idea is to make each term the same by substituting accordingly. For example, I can also make omega the subject here. So this is V over R. Then I can do two things, which is it's normally very convenient to convert and to write my kinetic energy in two alternative ways. I can substitute V equals R omega into here. So I get R squared omega squared plus a half I omega squared. But my line drawing is a little bit it's convenient to get each term in terms of the same quantity, either the linear velocity or the angular velocity. So that's one form, or we can have it, I can substitute omega equals V over R. Which one you substitute depends on what the question wants you to find. So I can also write it like this. So this is V squared over R squared. But I would suggest that you remember this one and you substitute, and you remember these formulas, of course. These ones you need to know off by heart, and you substitute these formulas accordingly. Let me clear this. Let me go back to my notes. This is what I did on the whiteboard for you, and these are the formulas written more neatly. And this is the total kinetic energy in words. Total kinetic energy of a rolling rigid object is the sum of the rotational kinetic energy about the center of mass and the translational kinetic energy. I've shortened my sentences a bit there. This is a general definition. This is not something that you're going to do in first year. So I think I'll just leave it up there for those of you that are interested, but it's not something that you're going to need for your quiz, and I think not for your exam either. And what I will show you is the definitions of torque in vector form. So let me go to the whiteboard again, and this will be the last thing I think I need to do with you. All right, so let's actually consider my vectors. Let me call this this is at right angles to the radius. Let me define a radius vector. and my linear force vector. Now you know that my torque is defined in magnitude as Fr, but this is only for the special case when F is at right angles to the radius. The definition that's more advanced, the vector definition, is R cross F. It's defined as the magnitude of R, the magnitude of F, sine theta. This is a unit vector that's perpendicular to the plane that contains R and F. But what I want to get from this is the direction of tau. You don't need to remember this, but what I do want you to remember is what this tells you is that the torque points upwards. Now the way to get this, and this is the part I want you to remember, is that you get the direction of tau from the right-hand rule. And the right-hand rule, I can't really draw it very well, but if you flatten your hand and point your fingers in the direction of R, and then curl your fingers towards F. If I rewrite this for you like this, maybe it'll be easier for you. Remember, I can move vectors around any way I want, as long as I don't change their direction. So I'm going to move this vector so the tails are touching. Now my right hand points in the direction of R, and I curl my fingers towards F, then my thumb will point in the direction of the torque. So all that the proper definition tells us, and the part of the general definition I want you to remember is that the torque is always perpendicular to the plane containing the vectors R and F, and it's given by the right-hand rule. Okay, let me just check I really have finished. This is for rotation in this direction. Try it yourselves and let F point the other way, and then see which direction torque goes. It's going to be in the opposite direction, but try and convince yourselves of that. I think this is a good place to stop. So I'll say bye-bye.